Alright, in this video we're going to go over Chapter 27, Linear Regression T-Tests. Linear Regression T-Tests. We want to test to see if there is an association between two quantitative variables, x and y. We look at a sample of data on a scatter plot and estimate the true relationship of the populations plot. The least squares regression line, that's for our sample, is y hat equals b sub o plus b sub 1x plus e sub I. Okay, b sub o is representing your sample intercept. B sub 1 is representing your sample slope, and e sub I is representing your errors or residuals. Okay, and a lot of these other formulas, these are going back to linear regression, so they're on your reference sheet. Population model, so that would be, we don't know this. Okay, this is what we're basing it on. We're making predictions with the sample to help us come up with a population model. Okay, is beta sub o plus beta sub 1 equals epsilon sub I. Okay, so beta sub o is the population intercept, beta sub 1 is your population slope, and epsilon I is the errors or residuals for the population. Alright, our residuals or errors are independent and normally distributed with a normal, a normal distribution of 0 and then the standard deviation of the errors. Okay, so to get the standard deviation of the errors, it's the summation of your errors squared over n minus 1, then take the square root. But your calculator will give you all of your residuals when you perform your linear regression t-test. A small standard deviation of residuals is 2. You can see how it's much tighter together, and then a larger standard error of the residuals of 10 is a lot more spread out. Alright, so t-test, testing the slope of the population of the regression line. Our hypothesis would be our null hypothesis, beta sub 1 is equal to 0. Now that's the population slope, so there's no linear association between x and y. My alternative would be that beta sub 1, the population slope, is less than, greater than, or not equal to 0, meaning there is a linear association between x and y. Our conditions are going to be a simple random sample. It's either stated or assumed. I have to have linear data, so I'm going to sketch a scatter plot that's linear with no outliers. It has to be independent, so each piece of data can be assumed to be independent of the other. I have to have normal residuals, so I'm going to make a normal probability plot of the residuals, and I want that to be linear. And then I want to have equal variance, meaning if I look at my residual plots, I don't want to see any patterns, so I don't want to show any change in the spread of the residuals. If all that's met, I can say conditions met. I'm doing a t-distribution, and I'm doing a linear regression t-test or a linear regression t-interval. The mechanics to get my test statistic t, it's going to be my statistic minus my parameter over the standard deviation of the statistic. That's what's on your formula sheet. Now what you have to use is your sample slope, which b1, minus your population slope, which we're assuming is 0, divided by your standard deviation. So then we can find our p-value. So the p-value is the probability that my test statistic is greater than or less than, depending on the test, whatever I get for t. Okay, your calculator will give you this value, but if you're doing it all using a table, you would do a t-CDF with your lower bound, upper bound, and degrees of freedom. Your degrees of freedom for these problems is n minus 2. Alright, our conclusion is going to be 3 sentences. We reject or we fail to reject the null hypothesis because our p-value is less than or greater than our alpha. We have sufficient or insufficient evidence that the slope of the population regression line is less than, greater than, or not equal to 0. Thus, as x increases, y either increases, decreases, or doesn't change. So as x increases, y increases will look something like this. As x increases, y decreases, looks something like this. And as x increases, y changes would just look a little different. All right, for a confidence interval, our formula is b sub 1 plus or minus t star times the standard deviation of b sub 1. Gives me my two values. My sentence would be that we are blank percent confident that as blank increases by x units, the blank increases or decreases between blank and blank y units. So in the first blank, you're talking about your x, whatever it is. Okay, make sure you use appropriate units. And in the next one, you're talking about whatever your y variable is, and make sure you refer to those units. So example, assume that we are told, so we're talking about airfare data. Assume we are told that 95% confidence interval for the slope was 0.05435 and 0.1804. So we could say we are 95% confident that as the distance increases by 1 mile, the airfare increases between $0.05435 and $0.1804. There are two ways to do the mechanics of the test. You can do it with actual data or with a computer output. All right, here's an example of a computer output. So what we need to be able to read this, so age of the wife, that would be our y variable. Then we have age of husband would be our x variable. And then our constant, the coefficient, 1.574, is our b sub o. And b sub 1 is 0.9112. All right, we're not going to use anything else from the constant row, but then everything else from age of husband, which is our x variable, gives us our standard deviation of b sub 1, gives me the t, gives me the p, okay, and then the equation, it looks like this kind of got screwed up. But then down in the bottom, it gives us our r squared value. Okay, we're not using the adjusted r squared, but the first one would be our r squared, and then the standard deviation of the errors would be the standard deviation for your residuals. All right, and then there's our formula. So we would have 0.9112 minus 0 over the standard error of b sub 1, which is 0.025, which gives me a t value of 35.249. If I plug that in to find my p-value, t has to be greater than that t-value, and I get a p-value of, 0.000, so basically 0. All right. Does a relationship exist between high school GPA and freshman year performance in college? A random sample of 40 freshmen at a local college was taken, and their high school GPA and GPA from their first full year were recorded. So n was 40. Degrees of freedom is 38 because it's n minus 2. My null hypothesis would be that the population slope is equal to 0, and my alternative would be that the population slope is not equal to 0, because they didn't say greater than or less. All right, so here's our computer output for freshman year GPA versus high school year GPA. So they gave us all the information we need in the computer output. They also gave us a scatter plot of the data, a normal probability plot of the residuals, and a residual plot. Okay, notice they have labeled the x and y axis. They've titled each graph because we have many, many graphs. And we also want to point out that we're talking about residuals for a normal probability plot. Okay, here's all our important pieces. You might want to label those. So freshman year GPA is our y variable. High school year GPA is our x variable. I have b sub o, b sub 1, the standard deviation, t and p, and then our r squared value. Now they want us to perform a test and complete an appropriate confidence interval. So my conditions, It was stated that it was a random sample. The scatter plot is approximately linear with no outliers. Remember, all of this stuff was given. Each student is assumed independent of the other. The normal probability plot is approximately linear, so normal residuals are assumed. The residual plot is scattered with no change in spread. So our conditions are met. We're doing a t-distribution, and we're doing a linear regression t-test. So my formula is t equals b sub 1 minus beta sub 1 over the standard deviation of b sub 1, which gives me, all of this is coming from that computer output, 1.0903 minus 0 over 0.2045, which gives me a t-value of 5.332. Again, I haven't done any actual work. I'm just writing all of this stuff down as work from my computer output. My p-value, we're doing a not equal to, so it's 2 times the probability that t is greater than 5.332, which is approximately 0. Therefore, we reject the null hypothesis because our p-value is less than our alpha of 0.05. We have sufficient evidence that the slope of the population regression line is not 0. Therefore, as high school GPA increases, the first year of college GPA changes. Now let's look at the confidence interval. So the formula is b sub 1 plus or minus t star times the standard deviation of b sub 1. Our alpha was 0.05. We were doing a not equal to test, and my confidence level was 95%. So b sub 1 and the standard deviation of b sub 1 are all coming from my computer output. T star I'm going to get using inverse t from my calculator, or we can write t star and then degrees of freedom was, I forget. So when I put that in, I get 2.024. Now I can add all the values and then subtract. So you're going to, might actually have to calculate these because I don't believe that that was given to you in your computer output. So multiply, then add it, and then subtract. All right, and we say that we are 95% confident that for every increase of 1 point of high school GPA, the college GPA increases between 0.6763 points and 1.5043 points. If I'm asked to do a problem where I have to use actual data, such as this example, I'm going to rely more heavily on my calculator. So, classified ads in a newspaper offered several used Toyota Corollas for sale. Listed below is the age of the car and the advertised prices. Is there a negative association between year and price? If so, estimate the slope using an appropriate confidence interval. So, I'm comparing age to price. My null hypothesis is that the slope for the population is equal to 0. My alternative is that the slope for the population is less than 0 because they said negative association. My conditions, I'm assuming the cars are representative. The scatter plot is linear, so there's no outliers. So first I would have to put all this data in my list 1, list 2. Then I'd have to make a scatter plot of list 1 and list 2. Then I'd actually have to run the test so that my calculator will make a list of the residuals. Then I can make a residual plot, and I can make a normal probability plot of the residuals. So each Corolla is independent of each other. The normal probability plot is linear, so we assume normal residuals. Now we're making a normal probability plot using the residual values. And then there's no change in the spread of the residual plot. So when we made a residual plot, here's what all my plots roughly looked like. Okay, so I made a scatter plot, a normal probability plot, and a residual plot. You might want to add it's a normal probability plot of the residuals, or label your x-axis as your residuals. Once our conditions have been met, we can say conditions met. We're using a t-distribution, and we're doing a linear regression t-interval. So now I can say that my alpha value is 0.05. I was doing a less than test. My confidence level was 90%, and my degrees of freedom is n minus 2, so 13. I'm doing a linear regression t-interval, which is b sub 1 plus or minus t star times the standard deviation of b sub 1. I'm doing that all in my calculator. I'm getting all these values, plugging them in. To get my t star, remember you have to go to inverse t, put in the area, and put in the degrees of freedom. So the area on one side of a normal model. So we're dealing with 90%, so we have 5% on both sides. And that gives us an interval of negative 1073 and negative 844.7. So we can say that we are 90% confident that for every 1 year older the car gets, the price decreases between $844.70 and $1,073.